In this problem, we're looking at an angle bracket with this load of P there at end A. On the other end of the angle bracket there at point C is a wire which is connected back to D. What we're doing here is trying to design the diameter of the wire and the diameter of the pin there at B. B is a double-sided connection. But we want to do this with a factor of safety on the wire of 3.3 and a factor of safety on the pin of 3.5, given what the yield strength is of the wire and the ultimate shear strength for the pin. So where we're going to go first, as always, is look at a free body diagram and then from that do equilibrium. The forces that are acting on our bracket is going to be the tension force there of FDC. We will have the reaction forces at B, By, and Bx. And then there is this applied force there, P, on the end at the angle of theta. I'm going to put x to the right. I'm going to put y up. I'm going to write down a moment equation about the pin joint there at B, where I've got F dc having a moment arm at B, and that's going to be in the negative k. I've got P, the only component that's which is going to give a moment about B is cosine of theta. That's going to have a moment arm of A, and there will be a plus sign here because that's in the plus k. So from that we see the load that's carried by the wire, FDC, is equal to the ratio of AB times P cosine. So that's the relationship between this load P and the reaction force that's carried through by that wire. I sum forces acting on this in x. Summation of forces in x, that's going to be a minus P sine theta plus Bx plus FDC equal to a 0. So it says then that the reaction force Bx, that's equal to P sine theta, minus FDC. FDC we saw was A over B P cosine. We sum forces in y. Summing forces in y, we get a minus P cosine theta plus By, and that is equal to 0. So when I solve for By, I see it's going to be a plus, because there already is a minus sign there, times P cosine of theta. So we have Bx and By as well as the load that's carried by that wire between C and D. So let's first look at pin B. Pin B is double-sided. So the shear force at B is shared between these two sides. So each side is going to be VB, and then there's going to be the load there B, where B is equal to the square root of Bx squared plus By squared. And so when I sum forces, I get that B minus 2BB is a 0. So the shear force on each side of that pin is equal to half of B, and that's the square root of Bx squared plus By squared. The shear stress in B, that's VB divided by the area of the pin, cross-sectional area of the pin, so that's pi dB over 2 squared, like that. So that's equal to 4 VB pi dB squared. And so we have VB there in terms of BX and BY, which we have already found. So then you look at the wire. The wire, we found what FBC was. Now when we look at the normal stress, that's going to be the load that's carried by that wire, which is FDC, divided by the area, which is 1/2 diameter of the wire divided by 2 squared pi. So that's equal to 4. Oops. I'm not quite sure where my 1/2 came here. This should just be a pi d over 2 squared. And so therefore that's equal to 4 FDC divided by pi dw squared, like that. So keep in mind that what we want is the factor of safety for the pen there at B. Factor of safety is going to be the allowable shear stress, which is equal to, I'll just say that that's tau allowable divided by tau B. So therefore, tau B is equal to tau allowable divided by factor of safety, which in the problem statement is called tau, Fs tau, whatever that number ends up being, and that's equal to 4b VB divided by pi dB squared. So from that we can solve for dB, for that factor of safety. So now for the wire, the factor of safety here is going to be the sigma allowable divided by the sigma in the wire. So let me just put a subscript of W there. So from here we see that sigma W, which is equal to the sigma allowable divided by factor of safety, which is Fs sigma. That must be equal to, from what we saw before, 4FDC divided by pi dW squared. So I guess one thing I didn't say, what I mean here by the allowable tau, is that's the allowable, that's the ultimate. We're designing the pin by the ultimate strength, whereas for the wire, we are more concerned about the change in length, the permanent set, and so there we're going to compare that with the yield strength there of sigma y. So from this, we can solve for dW. So here we had to do the usual stuff, the FBD, the equilibrium, and then we calculate the stresses, in this case for the double-sided connection. We calculated the normal stress there in the wire there, member CD, and then we put together factors of safety in order to get the correct expressions that we need here for our design values for diameter of the pin and for the diameter of the wire.